showing you the picture. I'm pretty sure you're all good at looking at graphs at this point and telling me what the limit is. So I'm not going to reintroduce the topic because you already know it, but for a lot of these, we might have to draw a graph of the function to the best of our ability. So find the vertical asymptotes, if any. So in a log graph, the log parent graph looks like this. We do have at least one asymptote, okay? Because you can only take the log of a, say it louder, Abby, positive. So this section needs to be positive, aka greater than 0. Now, interestingly enough, this is a quadratic inequality. So there are actually two different cutoffs. So if I go to solve this and I add 4 to both sides, I get that z squared has to be greater than 4. If you square root both sides, your two key points, and anytime we do a quadratic inequality, we really just set up a number line. Your two key points that will make it exactly equal to 4 are 2 and negative 2. And because it has to be greater than 4, those are open circles. We need to find out if this graph exists between those or outside of those. So which numbers, when you square, will give you something greater than 4? The numbers inside or the numbers outside? Aiden? Outside, like 3 squared, 4 squared, 5 squared, that'll all be bigger than 4. And negative 3 squared, negative 4 squared, negative 5 squared. So this graph's domain is all real numbers except the space between negative 2 and 2. Okay? So we actually have two vertical asymptotes, one at negative 2 and one at positive 2. Our graph is going to exist over here, and it's going to exist over here. Follow? So find the vertical asymptotes, if any, just to answer their question. X equals 2 and negative 2. They're not yet asking us for the limit as we approach those vertical asymptotes, but that's really where it will be heading. Okie doke? Okay. How about here? Tan of theta over theta. Where are their asymptotes here? Give me one place where you think there might be an asymptote name. 0, and what makes you say that? Can't be over 0. Sound logic. Where else might we have an asymptote, Olivia? Pi over 2, and what's the logic behind that? Tangent of pi over 2 is undefined. Where else would you think, Andrew? Three pi over 2. Could you keep going? What would be the pattern? How would we express it so that we could cover all of them? Odd multiples of pi over 2. So what if we said k pi over 2, where k is an odd integer? Okay, so it seems like those all logically make sense, and we know in a tangent graph that these pi's over 2 things are definitely asymptotes. My only somewhat concern is 0. 0 will definitely be an undefined point, but is it an asymptote? So if you're wrapping your head around tan over theta, just if you were playing around with this, tangent is sine over cosine, yes? All over theta. So a complex fraction like this, we could keep, change, flip. Keep, change, flip. And then I see this. In the world of limits, and we are thinking about what's happening at 0 here, correct? And the world of limits, what's the limit as you approach 0 on sine theta over theta? 1. So that might just be a hole and not an asymptote, right? Because if you look for your limit as theta approaches 0 on this sine, I'm going to give you the simplified version or the rearranged version. This portion, this sine theta over theta part, has a limit of 1. Which means then we're down to just really looking for the limit as theta approaches 0 for 1 over cosine. And what is the cosine of 0? 1. And what is 1 over 1? 1. And so your limit is actually 1 there. Your limit's never a numerical answer at an asymptote. Agreed? Asymptotes always have answers of does not exist, which leads us to an infinity or a negative infinity often. But it's never numerical. So that tells us right there that even though Nate's logic was good in that, yes, it's undefined there, it's not actually going to be an asymptote. Does that make sense? Here is that graph. You would never know how to draw that graph, but you can see all these vertical asymptotes at your odd pi's over 2. And you can see at 0, it's actually not an asymptote, it's rather a hole. Yes? With a limit of 1 at that. Okie doke? Just for the sake of showing it to you, here is that previous one, the natural log one, where the domain was that it only existed to the left of -2 and to the right of +2. So we do have 2 vertical asymptotes. The graph, you know, the computer graphics aren't that great, so you don't really see them as well, but they're there, okay, just by knowing what the nature of a log graph is, okay? All right, so figuring out where the asymptotes are, number 1, and then if you realize that what you're approaching is an asymptote, then you know that your answer to expect is either infinity or negative infinity, especially when you're coming from only one side. So if you think about a half, if I plug in an x of a half, what does this become? Pi over 2. And can we all agree that the tangent of pi over 2 is undefined due to an asymptote? Yes. So logically, we know that 1/2 is likely an asymptote. So now we just need to find out, well, if it's approaching it from the right, is it going towards positive infinity or negative infinity? So if you plug in something to the right of a half, is this part going to be positive or negative? Positive. Times, if you plug in something greater than a half to this, you're going to end up taking the tangent, and I'm going to go to the unit circle here, you're going to end up taking the tangent of something that's slightly over a half, correct? Which would put us in the second quadrant, right? Slightly over a half pi, put us in the second quadrant. Is tangent positive or negative there? Negative. And a positive times a negative is a negative. So negative infinity is your answer. Good? Zero from the right. From the right makes me think that there's a difference, right? Is it because of an asymptote? If I think about, and this is a composition of functions, we've got, what kind of function is that? Linear, quadratic, radical, rational, exponential. Do exponential functions have vertical asymptotes? No, they don't. Do sine functions have vertical asymptotes? No. So why they're asking about approaching this zero from the right might just be misleading. It might just be intentionally keeping you honest. Okay? So I would try to just plug in 0 and see if you can get just a direct evaluation answer. I'm leaning towards from the right or from the left might not even matter. So if I plug in a 0, I get, oops, why did I do that? What is e to the 0 power? 1. What's the sign of 0? So I'm just inclined to say they put that from the right there just to keep you honest. I don't think it made a bit of a difference. This is never going to be undefined, right? It's a continuous function no matter what. It's not a jump function, so we don't have to worry about that. And exponential functions are continuous. Sine functions are continuous everywhere, so there's never going to be a hole or a jump or anything. And again, no one would ever know what this function looks like because there's no such category that's like a cross hybrid between an exponential and a sine. But just for fun, this is what it would look like. So you can definitely see whether you're approaching 0 from the right or from the left makes no difference at all. It looks like it's kind of, it does like, it's got a lot of amplitude and then it pans out and flattens out. Interestingly, it does have a horizontal asymptote as you go towards positive infinity, but we don't have horizontal asymptote rules for stuff like that, so you'd never know that. Okie doke. All right, we're approaching -1 from the left. Now here, it's a little more feasible that -1 might be an asymptote, mainly because I know that secant graphs have asymptotes, right? Secant graphs are undefined and have asymptotes anywhere the cosine graph is 0. So we have 0, pi, 2 pi, and 0, -2 pi, -pi. So that's my cosine graph. So my secant graph is just going to continue in this pattern with asymptotes at pi over 2, 3 pi over 2. Again, those odd pi's over 2. Okay? So if I plug in a -1, can we confirm that that would create a negative pi over 2, which would be an asymptote? Yes? Okay? So if we are approaching, and again, this is a composition of a trig function and a linear function. If we are approaching -1 from the left on this secant graph, so that would make negative pi over 2, which would be here. We're approaching that from the left. So we have what kind of an answer? Negative infinity? Yes? Negative infinity. And then whether you're approaching on a linear from the left or from the right certainly makes no difference. So we can just plug -1 into there. It'll give us -2. And guess what? Negative infinity minus 2 is still negative infinity. Capiche? One over the cosine of pi x over 2 plus 2x. You ready for this? Oh dear. That is a funky looking graph. The fact of the matter is, here's -1. From the left, negative infinity. We're going to start graphing those next week. Just kidding. You didn't even bat an eye. I have no idea how to graph those, so good luck with that. All right. And the last one. Approaching 4 from the right. Again, this is very similar to that first one. With the natural log, we can only take the natural log of a positive. This is only going to be positive when x is greater than 4 or less than -4. Follow? So your two asymptotes are at 4 and at -4. But now the first one wasn't asking us for the limit. It was just asking us for where the asymptotes were. I'm going to put the -4 down there. So if we're approaching 4 from the right, we're plugging in something slightly bigger than 4, which when you square it will be ever so slightly bigger than 16. So that when you subtract 16, what's this approaching? If this is barely over 16, and the closer you get to 4, it'll be even more barely over 16. Do you follow what I'm saying there? So what's happening to this number? It's becoming what? Teeny tiny. Positive, right? The natural log of a tiny positive number. Think about your natural log parent graph. It's just like a log parent graph. If you're taking the log of a teeny, teeny, tiny positive number, what's your output? Trista? No? What'd you say? If I plug in a number as close as I possibly can to 0 to the right, what? No. What are my y coordinates here? Like if I were to draw a line as close to the y-axis as I possibly could, that would represent an x that's teeny tiny positive, right? What's the y coordinate of the graph there? Negative infinity. Yes. Negative infinity. Any questions? All right, true, false. Ooh. We'll take a vote in a moment. Number 1, true or false, that the graphs of polynomial functions have no vertical asymptotes. One is true, 2 is false. Not the answers. When you hold the number 1, that means that you're holding up true. If you hold up the number 2, that means you're holding up false. For number 1, hold up your answer on your mark, get set, go. Good, it's true. It's the only ones. Polynomial functions never have vertical asymptotes. That's correct. Good. Take a minute, think about number 2. Again, 1 is true, 2 is false. On your mark, get set, go. Good, it's true. If f has a vertical asymptote at x equals 0, then f has to be undefined there. That's true. You can never have a point on the vertical asymptote. Does that make sense? All right, bookwork. It's been a pleasure. Quizzes. Look at that. This class never timed out right, but So correction, well, there's no corrections, it's a quiz, but I will be recollecting these probably on, well, oh gosh, I don't want to take time away from your test. Be prepared for me to recollect them on Friday, and that's good because you definitely want to learn from your mistakes. Okay, thank you. There you are, dear. And these were out of 50. It's a very generous scale. Very generous. Although when I say that, it doesn't really make too much of a point difference. Like, if you did really well, it only like gives you a couple points. It really actually just squeezes everybody up. So if you did pretty terribly, you got a lot more than you deserve probably. It squeezes those thirds up.